The operating system is responsible for providing mechanisms for creating new processes and also terminating the processes when they fulfill their tasks or when they encounter errors. And also some other functionalities like, for example, communication between the processes, synchronization of processes with each other, and similar. So let's first focus on process creation. As we discussed earlier, when you boot an operating system, first the kernel is loaded, and when the kernel is fully loaded, what it does is it first creates a specific process. In the case of Unix-based systems, this process is called the init process. And the init process now starts creating the other processes, starting with the system services, but also the user programs and utilities. So therefore, the init process is, we say, the parent of the other processes, and each process can now become the parent of another process. So we talk about a parent-child relationship between these processes, and altogether, if you plot all these parent-child relationships, it forms a tree of processes. And this tree of processes is rooted at the init process, which is, once again, a very specific process. Each process has a unique identifier that's called the process ID, or in short, PID. So in a Unix system, for example, the tree of processes will look like this. At the very top, we have the init process, which has the process ID of 1. Since it's the first process to be created, it starts as 1. But the other processes will get their own process IDs as they're created. Therefore, when you when you start a system, the order of the processes creations could be slightly different. Therefore, since the orders are different, the processes may have different process IDs. So, except for the init process, do not depend on their process IDs. Anyways, here we don't, of course, see all of the processes because there are hundreds of them. So this is a simplified version, but init here has created the login process. Actually, there will be several login processes, one for each pseudo terminal. That means a terminal, a real one or a pseudo one, from which a user may log in. As you will see, there are many of them. The K-thread daemon for the kernel threads, and the SSH daemon, which is for the secure shell, used for remote connections in a secure manner. And there are also many other services, as I mentioned, but they're not shown in this simplified figure. So each of these processes, as we said, could create other processes, like the one in the middle, the kernel threads daemon, has created kernel helper and the PD flash processes with process IDs 6 and 200 for the sake of the example. But let's focus on, for example, the login process. The login process is the one that asks you the username and password. You enter your username and password. If the credentials are correct, that means the password matches the username, login will check this and from the etc password file, actually, it gets the usernames. So it checks whether there's really such a user in the system. And from the etc shadow file, it will get the password. Now, you might be a little bit surprised. The password is not taken from the password file, but it's taken from the shadow file. In the past, it was taken from the password file, but for the password file, it should be readable by everyone. So even if the passwords are encrypted, at least the encrypted versions would be visible. That's why in modern systems they're carried into the shadow file, which is only read only. But that's too much detail for the moment. But the important thing is it will get the login process will access the password and the shadow files to check if your username and password are correct. And if so, it will create a child process, which is your shell. Well, you could use different shells. It's the preference of the user. So you could use SH, CSH, TCSH, ZSH, Bash, Fish, whatever. There are many different shells. You could even write your own shell. So whichever shell you're using, it will learn that from the password file, and also learn your home directory again from the password file, and it will create your a child process which will be your shell. Okay, so in this example the user's shell is the bash program, so it runs the bash program as its child process. So again, in this example, the shell happened to the shell happened to take this PID. It could be different, as I said, and it is the shell that shows you the prompt. So at the prompt, you enter commands. For example, if you enter Emacs, it will run the Emacs program, which is actually an IDE, Integrated Development Environment, a programming interface. Or, for example, if you enter a command like PS, then it will run the PS program, which will list the processes in the system, either your processes or all processes, depending on the parameters. So these are all executed as separate processes that are actually the children of the bash program. Now, in this example, for example, PS and Emacs are running at the same time. So that's why bash has two children that are currently active. Now, when PS completes, it will be destroyed. That process will be removed from the system. But just at this snapshot, you have all of them. Here we say bash is the parent of PS and Emacs, or we say PS and Emacs are the children of bash, which is a child of login, which is a child of init. So init, pay attention, is the grandparent of all processes. Everything in the system at some point has rooted from the init process. Now, these processes, when they're created, they can use the resources of the parent, depending on whether the parent shares those resources with the child or not. The parent may share all of its resources with its children, or maybe a subset of them, or none of them. Okay, different ways of using them. And for the execution, the parent and the child process can run concurrently. That means at the same time they're both executing instructions. Or the parent might prefer to say, I will stop and wait until my child completes. When do we do that? Well, for example, if the parent needs the result of the child, it should not continue. It should wait until the child completes its task. Actually, in that case, the child is running for the parent. So when the child completes, the parent will be informed, and now it's sure that the child has completed, so it can check the results. The results are now stable since the child has terminated, and make use of those results and continue whatever it needs to do. So here actually we have an example of that. As we have discussed earlier, when we look at a process, remember the process's address space is composed of the text segment, which contains the executable binary instructions, the data segment, which is for the global variables, and the heap and stack, which share the same segment. Stack grows this way, heap, once again, and the heap grows this way. Remember this. Okay. Now, in your textbook, this thing was drawn upside down. It's the same thing. In the way I have drawn, the lower address values, address 0, which is the beginning for this process, is at the top, and the higher one at the bottom. In the figure that was upside down in our earlier slides, pay attention to that. Address 0 was at the bottom, so it depends on where you put 0 while you're drawing. I prefer to put it at the top. The book prefers it the other way around. Anyways, this is our parent process. When the parent creates a child process, it is yet another process in another address space. But the thing is, it copies everything from text here into here. So the whole text, in other words, the whole set of instructions in that program are copied as they are. The data segment is also copied as it is. So the global variables, for example, if there was a variable a here with the value 9, again a would be created here with the value 9, not with the initial value, with its current value, just at the moment the child process was created. And the heap and stack would be also exactly the same. So how do you create the child process? Remember, we earlier discussed that to create a child process you call fork. So in the heap here, you would have an entry for fork. Same is true here. There's also fork system call here. Function call there. Okay? So these are exactly the same. What are the differences? Well, first of all, since these are two separate processes, they have different process IDs. Let's assume this is because of my pen, sorry. Let's assume the parent had the process ID of 72 and the child had the process ID of 93. I'm just making up these numbers. Okay? So the only difference is that fork function returns to the parent the process ID of the child so that the parent knows who the child is. Because in the operating system there will be so many processes, so the parent needs to know who its child is. That's why it returns the process ID of the child to the parent, and again the operating system returns a different value to the child so that the child knows it's the child, it's not the parent. So if the operating system returned again another valid value like 72, if it had returned 72 to the child process, the child would think that it's the parent of 72, which is incorrect. Actually, it's the child of 72, not the parent. Therefore, it does not return the parent's process ID. Instead, it returns 0, which is an invalid process ID. So the child can know that this is invalid, therefore I should be the child. Now note that we didn't tell the child the process ID of the parent. Typically, the child does not need to know that. Now, in some specific cases, you may need to know it, but in general, it is the parent who needs to know who the child is, as we will see why soon. Therefore, it returns 0 to the child process. If the child process needs to know the parent's process ID, it can learn it by making use of other functions like get parent PID. It can get that, but normally we don't need that. So these are the two differences. They have different process IDs, and to the parent we return from fork the process ID of the child, and to the child we return only 0. Now the child processes, if it wants, it will be executing the instructions here, which are exactly the same as the instructions for the parent. Or one other thing, that the child process is able to do is it can delete everything in here. Okay, let me just erase all these. And it calls the system call named exec, giving as a parameter here the name of a program, whatever program is. Okay, just for the sake of the example, it could be bin ls or ps or a program you write, anything. So the operating system will replace now the text segment with the text of not the parent, but the text of the process that's mentioned here. So in the example, I said ls, so it will read the executable instructions for ls from the file named ls under the bin directory and put them in the text segment, create a data segment, initialize it with the globals of ls program, whatever it says, and create heap and stack. Okay? And this is actually how it will run. Still, pay attention, its process ID is 93. The process ID does not change. That's why the child is not destroyed and recreated. It's just the same process, but the instructions and the data segment heap stack, they change. So the memory space changes, but still it's a process with the same process ID. So that's what this exec call here does. Okay. So the child process will continue, and finally it will complete its task. So it will terminate by calling the exit system call. Either it gracefully terminates, or maybe it crashed. I don't know what happened. In both cases, the parent will get a signal saying your child has terminated. Now, if the parent had not said wait, it would have continued with the remaining instructions. But in this example, the parent has called wait. When the parent calls wait, it gets blocked. In other words, it starts sleeping until it receives a signal. And when the child terminates, it will receive that signal. It will understand that something has happened. It will, since it was waiting for a specific process ID, in this case it knows the child is 93, so it was waiting for 93. It will try to learn what happened to 93. Remember, with each process, we said we have a process control block. The parent also has its own process control block. For the parent, it would be process control block 72. For the child, it's 93. Now, when a process completes, its process control, for example, when the child completes, its memory space, all these would be released. Okay? So, it's all freed now from the memory, except for the process control block, which is stored in an operating system, the array, okay, not here in the process address space. Therefore, when the process exits and all its memory is released, memory, all the file handles, locks, whatever, everything is released except for the process control block. Now, that's important when we discuss the zombie processes. We'll come to that. Okay, but just keep this in mind. When the process terminates, the process control block is not released. Now, when the parent says wait, the operating system will give the information, return the information in the process control block of the child to the parent, and only after that PCB of the child is released. Now that means one thing, if the parent forgets to say wait, the process control block of the child will remain there. Till when? That we are going to discuss soon. So here we have the corresponding code. It's simple implementation of things we have discussed. As you can see, actually the implementation is quite easy. We're going to use the fork system call. And we're also going to make use of exec. Now note that this is exec LP. Actually, exec is a family of functions. There are different implementations of exec. They have different parameters. The parameters mean different things. So it is not at the moment very important which one we use. So we will just call this exec instead of exec LP. And we also have wait. Okay. Now, these three functions are in the Unix standard header file and the library. Therefore, you have to include the unist.h header file to be able to use these functions. So, at the moment, we just have the parent process. So, the parent process starts from main. It has a local variable named PID of type PID, which is actually a process identifier type. Actually, it's basically an integer class value. So the first thing it does is it calls the fork function. Okay, pay attention. Fork does not have any parameters, and it returns a PID value. Now, in the example we discussed for the parent process, let me draw once again. The parent was with the process ID 72. So for the parent, now this is heap and stack. Let me just write H and S for heap and stack. We are not doing memory allocations here, so heap will be actually empty. So let's just look at stack. So now we were in main, okay, and main calls fork. Fork executes, creates a child process. Sorry, my pen is once in a while making this strange lines. I'm sorry for that. In our example, the process ID was 93. For the text segment, it's again the same thing. By the way, what you have in text is actually the binary code for this program. It has some data segment again. Again, we don't have any globals in this data segment. And again, it has heap and stack. And the heap and stack is the exact copy. Sorry, let me write it here. We have main and fork. Okay. Just forget to draw one thing. Remember, PID was a local variable. So the local variables, remember, are on the stack. So to the parent process, what does fork return? Now, fork has created this child process, and fork returns to the parent process the process ID of the child, which is 93. So this one returns 93. Okay, and remember, for the child we said it returns 0. Now we're currently looking at the parent process. So it returns 93. So fork exits. Remember, what it returns is 93. So that return value is written here as 93. And for the case of the child process, it returns 0. So this will be 0. That's the difference. So this variable, because of the assignment here, we assign the return value of fork to PID. This variable is 93 in the case of parent and it's 0 in the case of child. Now the next thing we do is we look at this PID variable. Now, if the parent process was not able to create a child process, why would that happen? For example, you've created so many processes in the system that you cannot create yet another process. Okay, so in that case, that means you've exceeded the total number of processes you could create. In that case, it would return a negative value, typically -1. But that's an exceptional case. If that's so, it would be a negative value. So if it's negative, fork failed, which rarely happens, and you should exit from this process because you don't know what to do if you cannot create the child process. Okay, so we just say return and exit the whole program. Also note that we returned a value that's different from the default 0 to show that there is a problem. Okay, so if you get 1, you know that it's because you couldn't do fork. So if that problem does not occur, if you were able to create a child process, now for the current process, am I the parent process or the child process? I should be able to differentiate between the two because parent works one way, the child works the other way. So check if the return value is 0. If it's 0, that means you're the child process. If it's 1, you're the parent process. So let's first look at the child process. If the current process is a child process, that means we're executing this part. What we do is exec the ls program. So as I said, it will replace the text segment now with the text of ls. It will just read bin ls, and it will initialize the data segment for ls, and also the heap and stack are completely erased, and the main of the ls program will start running and do whatever it is supposed to do. Access the disk, get the directory information, learn about all the files in that directory, and prepare the output properly, and for each line use printf to display them on the screen, and then it will terminate. But while all these operations are being done, pay attention, it's possible that the operating system decides to give the CPU to other processes and possibly the parent process. That means the parent could go to the CPU before the child process completes. We cannot control this. Pay attention. You cannot tell the CPU scheduler to run the parent before or after the child process. It's not possible. It's up to the scheduler. If everyone would tell the scheduler what to do, then the scheduler could not optimize its own task. Okay, so it's a scheduler who decides. You never know how it will run. This is very important. Run the same program once again, you'll get different output. Every time you run the program, things could get executed in a different order because it also depends on all other processes running in the system. So you cannot control that. Therefore, in the case of the parent process, the first thing we do after fork, pay attention, in the case of parent, it will come to this else part, and the first thing it does is it says wait. Okay? You cannot control which process runs before or after the other, but when its turn comes, the parent says, I'm waiting. I'm not going to do anything. What does wait do? Wait says, I will not proceed. Make me sleep. Sleep till when? Well, sleep until I receive a signal, actually. So you block yourself as a parent. You block yourself. We say you're going to sleep on the event that a signal is received. Now, for the sake of simplicity here, the only signal that you could receive could be from the operating system telling you that your child has terminated. So if your child is still trying to display things on the screen, the parent is still in the sleeping phase. So it's in the wait queue. Remember the states and the queues, like we had the states like the new, running, waiting, terminated states. Here it would be in the waiting state. Waiting for what? Waiting for the signal about its child, which we call the sick child signal. The parent is sleeping. Therefore, the operating system might decide to run other processes, but at some point, the operating system will allow the child process to execute, and finally, the child process will be able to complete its task. It will display the information about all files in the directory and complete. And when the child completes, now the operating system sends a signal to the parent process, the sick child signal. The parent now wakes up from this wait system call, and it can now safely say the child completed. Okay? Because it knows that if the child had not complete, it would not be at printf, it would be at wait. Okay? So that's how things are running. Now, things are a little bit more complex than this. For example, here, when we said wait, we gave the parameter null, which means I'm waiting for any child. Now, in this example, there is a single child, so any child is the only child. But we will typically have parents with multiple children. So in that case, you might say, let me know when any of my children terminate. Or you might also say, let me know when specifically this child terminates. Okay? So it depends on what you're trying to do. So in that case, for example, we use wait PID instead of wait, because we also provide the PID, the process ID of the child. But this is basically explaining how things are working. So this slide is basically about what we have discussed. There is the exit system call when a process ends. So even if you don't say exit, the compiler will put that exit system call at the end of your main function. So every process typically exits. So return 0 at the end of the main function actually calls exit 0. But in C language, it's called return because main is also implemented as a function. You can remember in C, use exit anywhere. So even if you were inside another function, not the main function, but a function main called, if you call exit there, immediately the program terminates. And whatever parameter you have in exit, that will be the return value. And the child process, when you say exit, the operating system releases all resources. So it deallocates, in other words, all resources. The process is holding the memory, of course the CPU, any locks on devices or files. All files it says opened will be closed. We will later talk about pipes, for example. Any pipes or network connections will be closed. Everything will be released, except for, once again, the process control block. A process cannot release its own process control block. That process control block for the child is released only when the child has terminated and when its parent says, what happened to my child? Tell me about the exit of my child. At that moment, the operating system will give the contents of the process control block to the parent. Now there is no means of keeping that process control block anymore, because finally the parent has been informed about the status of its child when it had exited. Now the operating system removes the process control block. Okay, a process for which the process control block, the PCB, has not been released yet, which means the parent has not asked for that PCB yet. That process, although it has exited, all of its resources have been released. Since it still holds its PCB, actually the operating system is still holding its PCB for its parent, we say that process is in the zombie state. I'm not joking, by the way. Really, it's called zombie. So we say it's in the zombie state because it is at a state where it has died because it has terminated, but still there's something about it alive. Something has not disappeared, which is the PCB of that process. Only when the parent asks for the PCB will be released and the process will be gone. When you use the PS program to list the programs that are running, all other processes will be visible with their process IDs and other information. And these zombie processes, typically their process IDs names will be given in parentheses to show you that actually it has terminated, but it is in zombie state, to differentiate between the regular processes and the zombie processes. It is possible for a parent process to terminate its child process. Why? For example, it could be that, say, while your program is running, at some point you decide to run, for example, a very complex database query. Okay, it will take several minutes to run that query because you're really searching for something in a huge database. And meanwhile, as the values are found in the database that match that query, there could be several things. For example, when you do a search in Google, there are many things that match your expression, what you're searching for. Whatever search string you have, there could be many things that match that. So while it's going through the database, and whenever it finds something, it's displaying what it has found, you find what you're searching for, so you decide not to continue the rest of the search because you already found what you wanted. Like you were searching for, say, a file on the disk, and while it's searching for all files with that name, you found what you're searching for, so you say terminate the search. Now, the process could have created a child process that was doing the search, and since you say, I found what I'm looking for, you would like to kill that child process that's doing the search for you. Okay, and you could do that either by sending the kill signal, the kill signal, or there is a system call for that named abort, for the parent to abort its children. By the way, names like abort, kill, zombie, these are terrible names, I know, but that's how they're named. So it could be because the child has exceeded allocated resources, the task assigned to the child is no longer required, as in the example I gave, or the parent wants to exit. It's like you're killing the program that needed that search. So the search should also be terminated because the main thing is gone. Okay, so in such cases, you would like to exit. Now that could be, the parent process could be killed either because of the user wants to terminate the program, or the operating system may also be killing the parent. But one important thing is, typically on Unix systems, especially Unix, Linux, all of them, when the parent process is killed, all of its child processes should also be killed. Okay, because the child is typically related to the parent. If the parent is gone, whatever the child is doing, there's no one to take care of that. Therefore, when a parent process dies, all of its child processes die. When a child process dies, the children of the child process also die. Okay, that's what we call a cascaded termination. When a process dies, its children and their children, and their children. All that sub-tree in the process tree there, rooted at that specific parent process, will be killed. Now, there are ways of preserving the children. You want to kill the parent, but not the children. There are ways of dealing with that, but to do that, you should be able to disassociate the children from the parent, so that when you kill the parent, since the children do not belong to that parent anymore, they will not be used. Now, in the previous code, you have seen that we used wait. Normally, it takes a parameter. There we use null. That means we just wanted to know that the child had died. The child had terminated. Okay? So we did not need the PCB, therefore we returned null, so that wait does not return us anything because we are not going to use it. But if you want to learn that, you give the address of a status variable, and it will return information about the child's termination in that data structure. As we said, if the parent did not call zombie, if the parent did not call wait, until it calls wait, the child will be in zombie state. Until when? Until either when the parent calls wait, or when the parent dies. Remember, its children also die. So that zombie process in that case will be terminated, because the parent has disappeared. But normally what we expect is you should be calling wait to learn about your children, so that you don't leave so many zombies in the system. Because otherwise, if your processes, especially continuously producing children processes and then not getting their return values, your process table would be filled with zombie processes, something we don't want. You could be running out of space there. Therefore, normally you're expected to use wait. But even if you forget it, if the parent dies, as I said, the children also die. If the parent is terminated without invoking wait, that process is now an orphan. And as I said, in Unix systems, typically that would not be a problem because they will be terminated. One example use of all this is in the browsers, in the web browsers. Most of the web browsers in the past would be running as a single process. Many of them today are making use of threads. We'll come to visit that later in the following chapters. But for the moment, let's look at the older style, where all of them were a single process. There is a problem with this. If one of the websites causes a problem, especially a problem like an invalid pointer, which results in trying to access an invalid memory address. Therefore, you could receive a signal like segment violation, SIGSEG-V, in which case the operating system says this process tried to access an illegal memory area, so I'm going to kill that process because it tried to do something wrong. And if you let the process continue, now it has an invalid pointer, so it cannot properly work with that. So we don't know how the program will continue. So it's better to kill the process so that it doesn't do further damage to itself or other processes or the files. So if one of the websites caused such a problem, the whole browser would fail. So if you had many tabs open in the browser, all of them would disappear at the same time. Or if you had many windows, all of them would disappear at the same time. This is something we don't like. That's why actually most browsers have changed the design. But as I said, let's for the moment stick with that implementation. in that implementation for the Google Chrome browser, it had three different types of processes. One is the browser process, which is actually managing the user interface, the menu. You want to create tabs, you want to close tabs, that kind of information, the user interface. The disk access, you want to save to the disk or read from the disk. For example, you want to read an HTML file from the disk, whatever. And the network operations, communicating with the corresponding service. You try to connect to our university's website, department website, CNN.com, whatever. So the network communication. So to be able to access these servers, you should be sending network packets and receiving them. All these are managed by the browser. There is also the renderer process. Now, for example, you connect to our university's website and it sends you, say, index.html file. Now, that's an HTML hypertext meta language. So it has things like, you say you have the header, you have the body. Inside the body, you have the paragraphs, you have links, whatever. Somehow, someone should read that HTML code and display it as the web page, set the fonts, the colors, the links, whatever, all those. So it is the renderer because it does the rendering operation to a graphical readable website. If you have JavaScript code, for example, in the web page, do whatever JavaScript says. All that is done by the renderer. And a new renderer is created for each website that you open. There is a logic behind that because each one could be from a different site. If we did all of them in a single process, it would just they would just mingle from different websites. So it's better to have a new renderer for each website so that if this one has a problem, only that one fails. Nothing happens to the others. This is how the modern ones are now working. Now also one other thing is, as you know, the hackers typically try to attack through through the web pages that are showing to you. They are showing to you, well, it could appear very innocent, but there could be code behind, say a JavaScript running behind, that could try to steal information from your computer, from your files, or maybe steal information from the other tabs. Like you also log into your bank account or your email account and it's trying to steal your password from the other tabs. Or maybe not intentionally it's doing this, but it could do something wrong that could crash everything or harm your file system, whatever. So we typically run these codes in what we call a sandbox, which is a limited area, so that the application running there, the code running there, is not able to get out of that sandbox to harm the other parts. And that sandbox is something that would be typically erased when you're done with that tab. Therefore, if it tries to give a damage, it could damage only its own tab, but not the others. So it says when you're in the sandbox, it has very restricted disk access, restricted network access, or what we're trying to do is actually minimize the effects of security exploits. But still, since you have some network access and disk access, which you have to allow, you cannot completely prevent that. Otherwise, you couldn't save anything, you couldn't do any communications. Still, they try to find some exploits out of that, and we try to fix them. And the third process would be the plugin process, because you could have installed many plugins to your browser. So for each plugin, again, since these plugins are provided by different third parties, the plugins are run as separate processes to make sure that, again, they don't mingle with each other. Now, I've explained this for the Chrome browser. For the other browsers, the idea is the same.